Okay. Next is class B power amplifier. So in this configuration also, ഞാൻ അതിന്റെ സ്റ്റാർട്ടിംഗിൽ ഒരു ഇൻട്രൊഡക്ഷൻ പറയാണ്. ആക്ച്വലി നിങ്ങൾക്ക് അതിൽ പഠിക്കാനുള്ളത് ഇതിന്റെ സ്പെഷ്യൽ ടൈപ്പ് ഓഫ് കോൺഫിഗറേഷൻ ആണ്. അത് ഞാൻ പറയാം. ഓക്കെ. So simply, basically, what is a class B power amplifier? We can say a class B circuit provides an output signal varying over 1/2 of the input signal cycle, or we can say half of the input signal, or normally we are assuming a sinusoidal signal, so that we can say the total time period of a sinusoidal signal, that is, or total angle of the input signal is 360 degree. So here we can say for 180 degree of input signal, the transistor will be conducting. Okay. So generally half of our input will be available at the output. The reason is that in class B configuration, we are biasing our transistor in cutoff region. Okay. So our biasing point or our Q point is at cutoff. So here this is the Q point, right? Okay. So Q point is fixed at the cutoff point, so that half of the input cycle will be available at the output for class B power amplifier. Okay. So നിങ്ങൾക്ക് ഈ ഒരു DC load line ചെക്ക് ചെയ്താൽ കാണാൻ പറ്റും. Okay. This is our input signal. So here our Q point is fixed at this point, at cutoff point, so that this positive half of the input signal will be available at the output part. This negative signal or negative part, negative half cycle will be, it is not in the our operating region DC load line, so that it will be clipped off. So only positive half cycle will be available, right? Also, by considering the circuit, ഈ സർക്യൂട്ട് നിങ്ങൾ നോട്ട് ചെയ്യണ്ട കേട്ടോ. നിങ്ങൾക്ക് പഠിക്കാനുള്ളത് അതിന്റെ വേറൊരു കോൺഫിഗറേഷൻ ആണ്. ജസ്റ്റ് ഒരു ഐഡിയ കിട്ടാൻ വേണ്ടി പറഞ്ഞതാണ്. ഈ സർക്യൂട്ട് വരക്കണ്ട. നിങ്ങൾ ഈ ഒരു DC ലോഡ് ലൈൻ, ഓപ്പറേറ്റിംഗ് പോയിന്റ് ആൻഡ് ഇൻപുട്ട് ആൻഡ് ഔട്ട്പുട്ട് സിഗ്നലിന്റെ കൺസിഡറേഷൻ ഒന്ന് നോക്കിയാൽ മതി. ഓക്കെ. സോ ദിസ് ഇസ് അവർ ഇൻപുട്ട് സിഗ്നൽ. ഹാഫ് ഓഫ് ദ സിഗ്നൽ വിൽ ബി കട്ട് ഓഫ്. എന്തുകൊണ്ടാണ്? ബിക്കോസ് ഇഫ് യു ആർ അപ്ലൈങ് ദ ഇൻപുട്ട് സിഗ്നൽ, ദിസ് Q point will shift up and down. So while Q point shift upward direction, you will get this half of the input signal, but it couldn't shift to lower direction. Okay. So that part will be clipped off. Or by using transistor arrangement, we can say, since this transistor is in cutoff region, only for positive half cycle, only for this positive half cycle, this transistor will become forward biased. Okay. So that you will be available with this positive half. This is an NPN transistor, right? So when positive half cycle is here, we can say this is forward bias, and positive half will be appear at the output, right? And for the negative half cycle, this junction, that is this voltage VBE, okay, or we can say this input junction will be reverse biased, because to the P terminal we are applying this negative, right? So it will be reverse biased, so that this negative half will not be passed to the output. Okay. So something like half wave rectifier, we will get the output like this, similar to half wave rectifier. Also this considers the cutoff voltage, or that barrier potential is considered here. That is why this 0.7 volt. Okay. So that we'll discuss later. Simply we can say, for a single transistor, for a class B power amplifier using single transistor, you will get half of the input signal at the output. Or we can say the conduction angle is 180 degree for a class B power amplifier. Okay. So simply for NPN transistor, you can say during positive half cycle, this input junction or this base emitter junction will be forward biased, so that you will obtain this positive half cycle at the output. During negative half cycle, what will happen? Here it will be reverse biased, and the transistor will not conduct, and you will not be available with any output. So our output waveform is similar to half wave rectified output, right? So this is basically class B power amplifier. But actually, in our actual practice, we require both the half cycle, right? Here, we are only available with the information contained in one half cycle, right? So, in practical applications, we require both the half cycles. Also, we couldn't change the biasing point. For class B configuration, our biasing point should be at cutoff. Okay, so if your biasing point is at cutoff, you will obtain this 180-degree output only. So we have to go for another arrangement in order to get the complete input cycle. Okay, so we require complete information at the input signal. So we have to go for another configuration that is called push-pull amplifier. Okay, actually there are two arrangements. Push-pull amplifier is there, one complementary symmetry arrangement is there. നമുക്കത് പിന്നെ ഡിസ്കസ് ചെയ്യാം. So first is class B push-pull amplifier. Actually നിങ്ങളുടെ സിലബസ് സ്പെസിഫൈ ചെയ്തിട്ടത് class B push-pull amplifier ആണ്. Okay, so what is class B? ഇനി what will happen if we are not using push-pull configuration? അതൊക്കെ കറക്റ്റ് മനസ്സിലാകാൻ വേണ്ടിയിട്ടാണ് ഈ കാര്യം പറഞ്ഞത്. Okay, now coming to class B push-pull amplifier. Here, to obtain the output for full cycle of input signal, that is for all 360-degree of input signal, we should connect the class B amplifier in push-pull configuration. ഈ push-pull configuration ഒക്കെ എന്തുകൊണ്ടാണ് പറയുന്നത് നമുക്ക് വർക്കിംഗ് ഒക്കെ പറഞ്ഞു കഴിഞ്ഞിട്ട് പറയാം. Okay. Now, this in push-pull configuration, we require two transistors. Okay. In normal configuration, we are using a single transistor only, so that we are obtaining with the half cycles. So here we are using two transistors. These are connected such that each conduct on opposite half cycles. That is, we can say here you will be having two transistors. This upper transistor may conduct during positive half cycle of input signal, so that you will obtain positive half cycle at the output. Okay, and this lower part or this second transistor will conduct for this negative half cycle, so you will get that negative half cycle at the output. And to the load, you can combine these two and obtain the full cycle of input signal. Okay, so this is the concept of push-pull amplifier. So in push-pull configuration, we have to use two transistors. Here we are using two identical transistors. Okay, normally two identical NPN transistors are used. Okay, and you should connect it such that, or we have to connect in push-pull configuration such that one part of the circuit, or simply we can say one transistor will conduct for positive half cycle of input signal, and the second transistor will conduct for negative half cycle of input signal, such that we can arrange it in push-pull configuration, and you will obtain the complete input signal at the load. Okay. So by using this class B amplifier with the push-pull configuration, you can obtain low distortion, large AC output power, and high efficiency. Okay, so these are the advantages of this push-pull class B configuration: low distortion, large AC output power, and high efficiency. Okay, ഞാൻ പറയുന്നത് സ്പീഡ് ആകുന്നുണ്ടെങ്കിൽ പറയണേ. ഇത്രയും വരെ പറഞ്ഞത് ഓക്കെ ആണോ? Okay, സ്പീഡ് ആവുന്നുണ്ടെങ്കിൽ പറയണം. Okay, so now coming to the circuit diagram of class B push-pull amplifier. Actually, this circuit, as I already told, it consists of two transistors, Q1 and Q2. Both are NPN transistors. Okay, both are NPN transistor, and we are connecting together the emitter terminals, and it is connected to ground. Okay, or we can say it is connected to this point. Okay, ഇവിടെ രണ്ട് പോയിന്റും ഗ്രൗണ്ടിലാണ്. വേണമെങ്കിൽ അത് രണ്ടും കണക്ട് ചെയ്തിട്ട് കോമൺ ആയിട്ട് ഗ്രൗണ്ടിലേക്ക് കാണിക്കാം. അതിന്റെ റീസൺ ഞാൻ പറയാം. Okay, so it consists of two transistors Q1 and Q2. Both are identical. Both are NPN transistors, right? And we have two transformers. One is input transformers. Let us call it as T1, and there is an output transformer T2. These transformers are center tapped transformers. Okay, so in class B push-pull amplifier, we can say main components are, we have two transistors that are connected in push-pull configuration, and we can say you have two transformers. One is at the input side and other is at output side. Both are center tapped transformers. Okay, now you can take this circuit diagram. Signals ഇപ്പോൾ വരക്കണ്ട കേട്ടോ, ഞാൻ വർക്കിംഗ് എക്സ്പ്ലെയിൻ ചെയ്യുമ്പോൾ നിങ്ങൾ കൂടെ വരച്ചു പോയാൽ മതി. You can just take the circuit diagram, that is this input transformer T1, and here the secondary, that is the center terminal of the secondary is connected to ground, and here we are connecting this both emitter to ground, and the collector of these two transistors are connected to the primary of second out or output transformer. At this point we are connecting with the VCC. Okay. And from the secondary of output transformer we are taking the output. These signals ipo varakanda keto, you can just take the circuit diagram, that is two transformers and two transistors. Diagram copy ചെയ്തോ? Diagram copy ചെയ്തോ? Okay. Now see here, transformer T1. Transformer T1 is called phase splitter. Okay, it is called phase splitter. Why it is called so is, it produces two signal voltages which are out of phase with each other. That is, to the primary we are applying the input signal. ഞാൻ പറയുന്നതിന്റെ കൂടെ ആ സർക്യൂട്ട് സിഗ്നൽസും കൂടെ വരച്ചു പോയിക്കോട്ടോ. So this is our input signal. So at the primary of transformer 1 we are applying input signal. What we get at the output is, here we are connecting this center point to ground. Okay, so you will get the outputs at these two terminals of the secondary. You will get this input signal. Okay, you will get the input signal, but both will be out of phase. Actually you will get the exact input signal at these 2 points, but both are out of phase. So one will be like this, at this point the signal will be like this, and at this point it will be 180-degree phase shifted. Okay, so that is why this input transformer is called as phase splitter. So to the primary of input transformer we are applying the input signal, and at the secondary, that at the two terminals of the secondary you will obtain two identical signals which are out of phase, or we can say with a phase shift of 180-degree. Okay, now you can see what will happen during positive half cycle of input signal. Okay, I am considering the positive half cycle of input signal. So during positive half cycle of input signal you will get a positive signal at the base of Q1. Okay, and a negative signal, this half. Okay, negative signal at the base of Q2. Right, now one more thing you have to remember, when you are not applying any input signal, both these transistors will be at cutoff, because we are fixing by DC voltages, we are fixing our Q point at cutoff, right? So if there are any input signal, these both transistors will be in off condition. Our point on order, if you are not applying any input signal, the transistors Q1 and Q2 will be in off condition. Okay, അതിന്റെ ഒരു അഡ്വാൻറ്റേജ് എന്താണെന്ന് വെച്ച് കഴിഞ്ഞാൽ, here if you are applying not applying any input signal, the power consumed will be equal to 0. Okay, that is input signal apply ചെയ്തിട്ടില്ലെങ്കിൽ ഇവിടെ power wastage ഇല്ല. അതുകൊണ്ട് തന്നെയാണ് class B configurationന്റെ compared to class A നമുക്ക് efficiency increase ചെയ്യാൻ പറ്റും. Okay, in class A configuration our Q point is fixed at the middle of the load line. Okay, that means both the transistors will be on. So if you are not applying any input signal also, there will be wastage of power in class A configuration. Okay, but in class B configuration, since both the transistors are at cutoff, if you are not applying any input signal, there will not be any power dissipation, so that power wastage can be decreased. Okay, so in order to bias this transistor at cutoff, we are connecting like this, that is we are connecting emitter and base together. You can see this base is connected to this point, this is connected to ground, right? So this emitter is also connected to ground, so that we can say emitter and base are shorted initially, so there will not be, that is without input signal aanu parayunnathu, without input signal there will not be any current, so that we can say both transistors will be in off condition. Okay, so if there is no input signal, both transistors will be at cutoff, so we can say no power is wasted. So coming to the point, when input signal is applied, we can say at the secondary of this phase splitter, it develops two identical signals but out of phase with each other. Okay, now I am considering the positive half cycle. So during positive half cycle of input signal, what will happen? You will obtain a positive signal at the base of Q1, right? And a negative signal at the base of Q2. These both are NPN transistor, that is the base is p-type. So you can say during positive half cycle, this base emitter junction of Q1, initially it was in cutoff condition. So while you are applying positive signal, you will obtain a positive voltage at the base terminal, so that we can say this Q1, the base emitter junction of Q1 become forward biased, or we can say the transistor Q1 will be on. At the same time, what will happen to transistor Q2? Here to the P terminal, we are connecting some negative voltage, right? Some negative values appearing here, so that this is reverse biased. That means this Q2 will be off during positive half cycle. So during positive half cycle of input signal, we can say our transistor Q1 is on and Q2 is off. Okay, that means a current will flow through the collector terminal of Q1. I can say in this direction. Here we are applying VCC. Okay, VCC at this point, that is positive terminal of VCC at this point and negative to ground. Okay, so we can say our direction of current will be like this, say IC1. So as a result, IC1 will flows during positive half cycle. Okay, and during negative half cycle, what will happen? The reverse of this, that is during negative half cycle of input signal, that is during this negative half cycle, what will happen? Here you will get negative signal, here phase shifted version, so that here you will get positive signal. Okay, now since here it is negative signal, we can say this base emitter junction is reverse biased, or this transistor will become off. Here to the Q2 we have positive half cycle, positive value, so that this will be forward biased. Okay, so this will be forward biased, so this Q2 will become on, so that we can say a current will flow through this circuit, that is IC2. Okay, that current will flow through this circuit. So actually this current will be available here. You will at the primary of this second output transformer, you are available with both these currents, right? So here you will be a wave like this, and here it will be like this, because this is in common emitter configuration. So here and then down there will be a phase shift. So here during positive half cycle, which is conducting, means you will obtain a wave like this. Okay, and here during negative half cycle, you will get a wave like this here. Okay, so at the output transformer, the function of the output transformer is that to combine these two signals, that is you are available with the 2 signals at the primary of this transformer. So this output transformer is used to combine both these signals and produce the complete cycle of output signal. Okay, so output transformer join the 2 halves of this primary input signals, or we can say collector current, and produce a full sinusoidal wave at the load resistor. Okay, so this is the operation of class B push-pull amplifier. I'll repeat. So നോക്ക് ഒന്നുകൂടെ നോക്ക്, ഡയഗ്രാം നിങ്ങളുടെ ബുക്കിലുള്ളത് റെഫർ ചെയ്യാം. ഒരു സെക്കൻഡ് സിസ്റ്റം. So ഒന്നുകൂടെ നോക്ക് അതിന്റെ വർക്കിംഗ്. The input transformer or phase splitter convert the input signal to 2 out of phase signals. That are both are identical signal, but there will be a phase shift of 180 degree. And the output transformer combines the signal from the collector to the load. Okay. The transistors Q1 and Q2 are biased at cutoff by providing zero bias on the base. Okay. Zero bias on the base is provided by short circuiting the emitter and base, right? Then we can say when there is no input signal, both transistors will be off. Hence, no power is wasted under zero signal condition. That is, we are biasing both the transistors in cutoff region so that there will not be any power wastage during zero signal condition. That is, if we are not applying any input signal, there will not be any power dissipation. That's the reason in class A amplifier, we are biasing at the midpoint of load line so that the transistors will be on. Okay. So if you are not applying any input signal also, there will be some power dissipation in the transistor. That is why that efficiency is, maximum efficiency is 50% in class A amplifier. Okay. So here when there is no input signal, both transistor will be off. So no power is wasted under zero signal condition. Okay. Then when an input signal is applied, 2 signals which are identical to each other but out of phase are developed at the secondary of the transformer 1 or the phase splitter. Okay. When the signal on the transistor, note diagram nokka, when the signal on the transistor Q1 is positive, that is during positive half cycle, the signal on the Q2 is negative by an equal amount. Okay. So during first half cycle, that is during positive half cycle of input, transistor Q1 is driven into conduction. That is, it will turns on, whereas transistor Q2 is driven off. Okay. Then the current IC1 will flow through the transformer. That is നമ്മുടെ Q1 in the collector terminal, result in first half cycle of the signal to the load. Okay. Then during the second half cycle of operation, what will happen? The transistor Q2 is driven into conduction. That is, the transistor Q2 will turns on, whereas the transistor Q1 will be in off condition. As a result, the current IC2 will flow. That is from the collector of the transistor, we can say it is coupled to the transformer. That will result in the second half cycle of signal to the load. Okay. So the overall signal developed across the load then varies over the full cycle of input operation, signal operation. That is, for the complete input signal, we can get the output by using this push-pull configuration. Okay. And why we are calling it as push-pull circuit? Since one part of the circuit pushes the signal high during one half cycle, and the other part pull the signal low during the other half cycle, right? So that we are calling it as push-pull circuit. Okay, that is during positive half cycle, the upper transistor pushes the signal to high. Okay, and during negative half cycle, the lower transistor pulls the signal to low value, so that you will obtain complete a signal at the output. That is why we are calling it as push-pull circuit. Okay, working clear ആണോ ഇത്രയും പറഞ്ഞത്? ക്ലാസ് ബി പുഷ്-പുൾ ആംപ്ലിഫയർ മിക്കവാറും ചോദിക്കുന്നതാണ്. Okay, now coming to the efficiency of this class B amplifier. It is more than class A amplifier. Okay, so now we can see how much is the efficiency. Using class A configuration in resistive load, we can obtain maximum 25% efficiency. By using transformer coupled load, we can obtain an efficiency of 50%. Now we can see what is the efficiency of this class B power amplifier. One more thing, class B il ningal single transistor use cheyidalum ee push pull configuration ayalum efficiency same thaneyana keട്ടോ. Class B amplifier inde efficiency ഏത് configuration ഇനി ഒരു configuration കൂടെ ഉണ്ട് class B യിൽ ഏത് configuration ആയാലും നിങ്ങൾ efficiency ചോദിച്ചാൽ ഈ ഒരു analysis derivation തന്നെയാണ് ചെയ്യേണ്ടത്. Okay, so efficiency, what was our efficiency? Efficiency is equal to, generally we can say it is the ratio of output AC power to the input DC power, right? So efficiency is P out AC divided by P in DC, right? This is the equation for efficiency. Now we can consider the input and output power. So the input AC power is given by, first the input DC power, the input DC power. Input DC power is given by P in DC, that is equal to VCC, that is supply voltage, into IDC, that is DC current flowing through the circuit. Okay, DC current flowing through the circuit means that is this IDC is the average or DC current, average or DC current taken from the supply VCC. Okay, taken from DC supply, that is DC supply voltage is VCC, that is IDC is the average or DC current taken from the supply VCC. Okay, so we have two transistors here, right? So this DC current or this IDC drawn by a single transistor. A single transistor is given by IDC equal to IC max divided by pi. Okay, so maximum collector current divided by pi, that is the DC current. DC value അല്ലെങ്കിൽ average value നിങ്ങൾ പഠിച്ചിട്ടുണ്ടാവും അല്ലേ? It is the maximum value divided by pi. RMS value, maximum value divided by √2 എന്നൊക്കെ പഠിച്ചിട്ടുണ്ടല്ലോ. So DC, we can say the current, DC current drawn by a single transistor is given by IDC is equal to IC max divided by pi. Hence, the total DC power drawn. We have two transistors, right? So we have two transistors, so that we can say total DC power drawn will be equal to total DC power drawn from AC is it is equal to what? It is actually total DC current. Total IDC will be, for a single transistor it is IC max divided by pi. Okay, for two transistors it will be what? 2 times IC max divided by pi. Okay, hence we can say the total DC power drawn, that is our P in DC, it will be equal to this VCC into IDC, right? So this VCC into IDC means IC max divided by pi. This is from a single transistor, we can get IC max divided by pi. We are using two transistors here. So we can say it is 2 into IC max divided by pi. Okay. With actually single transistor in the case, IDC and here you are using two transistors so that our IDC is equal to 2 into IC max divided by pi. So this is our input to DC power, VCC into, or we can say 2 into VCC into IC max divided by pi. Okay. Now coming to the AC output power. AC output power, that is P out AC. That is equal to what? As in the earlier case, it is Vrms into Irms. In the case of AC signal, we are considering RMS values, so that Vrms into Irms. So Vrms means maximum VCC divided by root 2, and Irms is equal to IC max, maximum collector current divided by root 2. Or we can say it is VCC into IC max divided by root 2 into root 2 means it is 2. So this is output AC power. Okay. And now substitute this equation 2 and, sorry, this is 3. Equation 2 and 3 in equation 1. So you will get efficiency. Efficiency is equal to P out AC divided by P in DC. That is, P out AC means it is VCC into IC max divided by 2, whole divided by P in DC. P in DC, here you have 2 into VCC into IC max divided by pi, right? So 2 into VCC into IC max divided by pi. Okay. So what will get? This VCC will get cancelled, right? And this IC max, that will get cancelled. So you will, what you will get? It is actually 1 by 2 divided by 2 by pi. This is 1 by 2 divided by 2 by pi. Or we can say it is equal to what? Pi by 4. Right? It is pi by 4. So pi by 4. Simply pi to 3.14 substitute on change. Okay. What is this pi by 4 value? Not that angle rate, not in degree. Pi is equal to 3.4. Then pi by 4, what will get? You will get it is 0.785. So calculate it. So that we can say efficiency in percentage. We are applying. We are representing efficiency. So this will be into 100. That will be equal to 78.5%. Okay, 78.5%. This is the maximum possible efficiency using this class B amplifier. Class B le ഏത് configuration ആയാലും ഇത് തന്നെയാണ് കേട്ടോ. Class B power amplifier le efficiency equal to 78.5%. That is, compared to class A, high efficiency will be provided. High efficiency means what? We can convert, that is, efficiency means P out AC by P in DC. So power conversion efficiency means how much power, that is, at the input we are applying, we are available with DC power. So we are converting this DC power into AC power, right? So maximum efficiency means we have to convert complete DC power into AC. So practically നമുക്ക് ഒരിക്കലും 100% efficiency possible അല്ല. There will be power wastage. So here we can obtain 78.5% of efficiency. And കൂടെ ഒരു equation കൂടെ note ചെയ്തോ. The maximum power delivered to the load. That maximum power is given by VCC square divided by 2 into RL. The maximum power transfer theorem obtained in equation. Okay. The problem വന്നിട്ടുണ്ടെങ്കിൽ ചിലപ്പോൾ ആവശ്യം വരും. അതുകൊണ്ട് ആ ഇക്വേഷൻ കൂടെ ഒന്ന് നോട്ട് ചെയ്യാം. Maximum power delivered will be equal to VCC square divided by 2RL. Okay. Efficiency clear ആണോ? Efficiency of class B power amplifier is 78.5%. This is the maximum possible efficiency. Practically, it will be less than that. Okay. Clear or no? Okay. നെക്സ്റ്റ് നമുക്ക് പറയാനുള്ളത് ജസ്റ്റ് എന്താന്ന് മാത്രം പറയാം. നെക്സ്റ്റ് ക്ലാസ്സിൽ ഡിസ്കസ് ചെയ്യാം. Crossover distortion. It is actually one of the major drawback of class B push-pull configuration. Okay, one of the major drawback of class B push-pull configuration is that crossover distortion. We have discussed the advantages, that low distortion, that is actually harmonic distortion. Low distortion, high efficiency, large output power. That are all the advantages of this class B configuration. But coming to the drawback, the main drawback is crossover distortion. Okay, so we will discuss this crossover distortion in the next class.